Okay, let's dive right into this explainer and uncover a single, profound logical trick that runs through literally all of theoretical computer science. It's a concept that completely bounds modern AI. Honestly, understanding this completely redefines how we think about the limits of computation. And by the end of this, you're going to see all those massive AI safety debates we're having in 2025 in a completely new light. Here's our roadmap for today. First, we'll cover the universal proof skeleton. Second, hitting the five walls. Third, the AI safety collision. And finally, we'll wrap up with navigating structural limits. So, Section 1, the universal proof skeleton, the logical trick behind everything. Before we can truly grasp the limits of AI, we really have to uncover this master key. There is this one single logical trick that brilliant minds have used repeatedly throughout history. It goes like this. Step 1, you assume a universal solver exists. Step 2, you construct a self-referential input. Basically, you ask the solver about itself. Step 3, you show that this forces the solver to answer A and not A at the exact same time. And step 4, well, that's a contradiction. It means the solver literally cannot exist. The big takeaway here, the more a formal system can express, the more inescapable mathematical barriers it hits. It's wild to see how this builds historically. We're talking about giants here, from Gödel in 1931 to Turing, Cook and Karp, Vapnik, and Landauer. This identical four-step proof structure has dictated the boundaries of reality across 5 distinct eras and 5 totally different fields. And it's this exact progression that leads us right to the doorstep of modern AI. Moving on to Section 2, hitting the 5 walls. Same trick, different costume. Now we're going to take that exact same 4-step skeleton we just talked about and use it to uncover the 5 absolute limits of reasoning. Let's start with wall 1. Logic. Back in 1931, Kurt Gödel asked a seemingly simple question. Can a sufficiently powerful mathematical system prove every true statement about itself? Using our skeleton, Gödel constructed a self-referential arithmetic sentence that effectively says, I am not provable. This creates a total dilemma, right? Because if the system proves it, it proved something false. But if it can't prove it, there's a true statement it completely missed. So, the absolutely crucial point here is that mathematical completeness is impossible. Your formal system is always going to have unprovable truths built into its very architecture. It's not that we're just too lazy to find the proof. It's that no proof exists within the system itself. Logic, fundamentally, is bounded. And that brings us to wall 2, computability. In 1936, Alan Turing applied this exact same trick to programs. He asked if a solver could exist that reads any program and decides if it will eventually halt or if it'll just run forever in a loop. Turing imagined a program evaluating itself. He designed it so that if the universal solver predicts it halts, the program deliberately loops. If the solver predicts it loops, the program halts. Boom. A classic, unavoidable contradiction. And the consequence of this? This wall means that global semantic properties of programs are entirely undecidable. Meaning, knowing with absolute mathematical certainty what an arbitrary program, or say a massive modern neural network, will do in every single situation is fundamentally impossible. Not just hard, I mean mathematically impossible. But okay, what if we restrict things? Welcome to Wall 3. Complexity, established by Cook and Karp in 1971. Even when a problem is technically solvable, that self-reference trick subtly encodes other hard problems into it. For instance, verifying the safety properties of a finite neural network is what computer scientists call CoNT hard. In plain English, that means the time it takes to solve skills so poorly, it practically becomes impossible. Which hits us with this wall. Efficient verification of arbitrary neural networks has an absolute speed limit. You really can't just throw raw compute at verifying arbitrary AI and expect a quick guarantee. You have to restrict the system, exploit specific structures, and make it mathematically tractable. Otherwise, you'll literally run out of time before the universe ends. Wall 4 takes us into the realm of machine learning with Vapnik. Here we're looking at something called VC dimension, which measures the maximum expressivity of a model. The self-referential trap here is that a highly expressive model can perfectly shatter and memorize any finite dataset you give it, while at the same time learning absolutely nothing about the actual underlying reality. The hard limit we hit here is information theoretic. Just having a massive mountain-sized pile of data is not enough to guarantee an AI will actually generalize safely to the real world. You simply cannot learn some patterns from finite observation alone. You absolutely have to add domain knowledge and inductive bias. Finally, we reach wall 5, physics, discovered by Landauer. Let's say you perfectly navigate the logic, the computability, the complexity, and the learning math. You do everything right. Well, the physical universe still steps in to demand its toll. Every single time a computer erases just one bit of information, thermodynamics dictates it must release a specific amount of heat, kT, natural log of 2 joules, into the environment. Computation is not free. Thinking has a physical cost. You cannot build an infinitely efficient reasoner. Every bit of precision you demand, every absolute guarantee you want from an AI, inherently costs massive amounts of physical energy and computation. That thermodynamic floor, it's absolutely real. All right, Section 3. The AI safety collision, the hardest problems of 2025. You know, every major AI safety debate you read about in the news today isn't actually a new engineering challenge. It's secretly a direct head-on collision with one of these 5 historical walls. Take this specific demand. Can we build an AI that is provably safe? People constantly demand absolute, guaranteed safety from human-level AI. But as we've just seen in this explainer, that is entirely the wrong mathematical question to ask. Because any system powerful enough to model human reasoning is powerful enough to express self-referential concepts. Gödel's wall proves there will be safety properties it can't prove about itself, and Turing's wall proves its behaviors are completely undecidable in advance. Complete safety in full generality is just mathematically impossible. We can only ever achieve safety guarantees in tightly restricted, very specific domains. Here's another massive debate happening right now. Will scaling solve alignment? Like, will simply making a large language model bigger, adding billions more parameters, and throwing more training data at it automatically make it safer and better aligned with human values? And our 5 walls brilliantly illustrate exactly why the answer is no. Wall 4 shows us that scaling a model increases its expressivity, its VC dimension. But here's the catch. As expressivity goes up, your mathematically guaranteed learning safeguards actually get weaker. They don't get stronger. Scaling gives an AI more capability, sure, but it does not automatically give alignment unless you deliberately bake in specific domain knowledge. Which brings us to Section 4, navigating these structural limits, because you do not break the walls. We simply cannot brute force our way through these theorems with just a billion more GPUs or a trillion more data points. We have to play by the rules of the universe. Expressivity forces obstruction. This is the grand unifying principle behind everything we've looked at today. The more capable and expressive an AI becomes, the more fundamental mathematical barriers it inevitably hits. It's not a bug in the code, folks. It is the deepest theorem we have about formal reasoning. So, how do we actually move forward? Well, the best engineers don't fight the math. Instead, they successfully navigate between the walls by carefully asking structural questions. They ask, is this specific problem strictly decidable? Is this exact model class learnable? Is verification actually tractable on this architecture? They look at what guarantees are actually achievable given those structural limits. Which brings us to a final thought to leave you with. As we continue to build this incredible future of reasoning systems, and as AI becomes deeply integrated into our everyday lives, ask yourself, which inescapable law of logic are you brushing up against today? Because truly understanding the limits of our technology is the very first step to mastering it.